All right, good day, everyone. This is Fred Schenkelberg, and welcome to today's uh, Ascendo Reliability webinar. And this is in the monthly series that I've been doing. I've just realized it's been a bit over 3 years now, I think, or maybe a little longer. I've been involved with webinars in one form or another for many, many years, even and used all kinds of different systems. So I've enjoyed this one, and I enjoyed the amount of interaction and the ability to chat and to ask questions and get people involved and stuff like that. Had a pretty good turnout for today, so I expect quite a few people online and expect a lot of sharing of information in the chat window and through the presentation. And so today I want to talk about some of the basics or the base parts of root cause analysis. Now, of course, this could be a whole you could get an advanced degree in this with many, many different credit hours and lots of hours spent on it. Or you could spend a career doing nothing but failure analysis, which is a part of root cause analysis. But I wanted to talk about some of the basics of this and some of the structure around being able to do it very effectively. So on occasion, and I laughingly say it's what keeps us in business, is something fails. And part of this is also knowing, well, what is it about a failure that we can do something to improve it? You know, what's the nature of this failure such that we can avoid it in the future or minimize the damage it causes or do something productive about a failure actually occurring. But first, we really need to understand what's going on, what is actually happening, such that the results we wanted, the product performing as expected, the equipment operating when expected, the throughput to be as high as we need it to be, the customer to get the functionality they were expecting. When that doesn't happen, we need to know why. And you've all heard of the 5 whys, I'm sure. It's the heart of what this root cause analysis is about, is, well, what happened such that something failed? And with that level of understanding, then we can actually fix the problem. We can create a solution that fixes it once. And you've seen the issue where you implement a solution that you think is going to solve it without basically the fundamental understanding you need to determine that. And 2 weeks later, the same problem is occurring. And it comes from the fact that each failure that we do observe, the symptoms that our customers experience, may be caused by many different fundamental problems. So like a computer not powering on could be a bad power supply. It could be that there's no electricity available in the wall socket. It could be a problem on the motherboard. It could be on and on and on. That list gets long very quickly. And so which one do we fix? Which one do we actually solve? And that's the heart of root cause analysis, is really to get us to a point where we can do something to restore a system or prevent future systems from failing. All right, so let me back up a little bit. What counts as a failure? So this is a chance to exercise the chat window. What do you count, or what do you define as a failure that would warrant doing a root cause analysis? Yeah, Mark's saying it's when the customer says it's a failure. Brian's talking about it's not able to function within tolerance. So it could be working, but not quite fast enough, not quite well enough. Maybe a forklift isn't able to lift the load that it was designed to do, something like that. Okay, not getting the expected result. That one is similar to when a customer says it failures, because if I expect my computer on my desk to make me coffee in the morning, is that a failure? Well, if that expectation is there, some would argue that it is a failure. It wasn't designed to actually make coffee in the morning. I don't know if I'd really want hot liquid and coffee coming out of my computer system, but there's enough heat in there that it might actually make it pretty well. No longer inspect. Now, this is similar. I'm seeing some of the definitions that are similar to what we define quality as, right? It's there's a whole realm of it's in specification or as designed or so on. Well, and then there's other parts that allude to more, is it the right design, right? They have a bad experience or it's not as expected and so on. Yeah, Keith, that's an interesting take on it. It's and we don't know why. It's still a failure, I think, even after we understand what exactly caused the failure to happen and why it happened, whether it's a part of our design process and understanding our customers' expectations or requirements, or it was a manufacturing error, or it was an installation damage, or it was a wear out. Whatever the underlying fundamental reason was, if it fails, it still fails. And I think it's counted that way. I like to summarize this as a failure is anything that costs you money, right? Some failures really don't count because nobody cares. If a component is scratched on the interior surface of your computer, and it's not going to lead to a dielectric breakdown or an increase in contamination or anything. It's just a visual defect on a component that doesn't impact its functionality. I'm trying to pick a type of issue that, in some cases, in a factory, if I saw that scratch, I would probably discard that component and go look at my process to minimize the amount of scratches on components, for example. Maybe it's on the markings on the component to tell what it is, and it occludes it slightly. At that level, it might be considered a failure, and we need to deal with it. On another level, once it's in a machine and working and nobody really can see it, is it a failure? Do we really need to count that? If a customer calls, or if a repair person calls and says, hey, I can't read this component, that call center call costs us money. The product return costs us money. The loss of future sales, because they're saying, hey, you make products that have damage internally, then that's a failure. That costs us money. So there's many ways that a failure can cost us money. We may not even know about it. If a customer doesn't get the performance they really expected from a product and wasn't designed even to do that, well, they don't buy your future products. They don't tell their friends that this is the solution for you, so you lose the word of mouth part of it. So I expand it, as many of you have done here, is a failure is in the hand or in the mind of the customer. They really define it. And when their definition of failure costs you and your organization the ability to meet your business objectives, commonly profitability, then that's a failure. And it could be hardware, it could be software, it could be it didn't have the right features designed into it. It could be the wrong color, for example. We did a marketing error and picked a particularly poor choice for color, and it doesn't gain market acceptance because of that. Those are all parts and pieces to it. And so in my work as a reliability engineer, we often work with the engineering requirements document and the specifications from vendors and so on. And it's not always a hard and fast rule that this is a failure and this isn't. there's gradations of that. And it is a complicated question oftentimes. But at the grandest level, failure is something that essentially doesn't work as expected from the customer's definition, and they call, they return it, or they don't buy anymore, or they give us a bad Yelp review, or whatever. It costs us some money in some way, is a simple way to do it. Yeah, and I don't think there's anything wrong with focusing in on the specification side of it, yet I think you should expand that a little bit. Products can be in or out of specification and still be considered a failure by your customer, right? If they are expecting a printer to print 10 pages per minute, because it says so on the side of the box, and then the types of documents they actually print only achieve 8 pages per minute, then we count that as a failure. The specification is under specific conditions. You're printing black and white and blah, 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 and low humidity and all these other conditions that are on it, all the fine print. And they say it could print up to 10 pages per minute. Well, if that gets interpreted that I expect 10 pages per minute, we set the wrong expectations. And then it's counted as a failure because they return the product, for example. Still costs us money. Nothing to do with the hardware and so on, but it's an expansion of what we typically call failures. Now, there's plenty of challenges to doing root cause analysis. I wanted to quickly explore a couple of these and then go back to you and ask what kind of challenges you're facing. We'll talk about dealing with each of these in a quick way, in a short way, in a short discussion. And I'm sure you've seen all of these, maybe even these characters around the table with you at one stage or another. So a failure occurs, right? The plant goes down, a piece of equipment in the production line stops working, say a welder in an automobile factory. And all of a sudden, the operations manager is on the phone and calling everybody and walking down the line and harassing our technicians or trying to figure out what went wrong. And they want it running now. And they're very quick at reminding us that every minute it's down, it costs us so many dollars of lost production. And there can be immense pressure to fix it now. And whether we stop production or it is a product that's in a critical functionality for a customer and they're upset that it fails and they need a patch or a fix or a replacement immediately. There's all kinds of products that are out there that when they fail, it costs our customers or our factory immediate consequences. And so the phone calls and the urgency and the pressure can mount to be quite a bit of just get it fixed. And you see quick fixes, patches, half-done things. What can we do right now to get up and running again? So it's baling wire and duct tape and quick patches and fixes and that may or may not actually solve the problem, but they get it up and running again. You know, maybe it's just restart the system and hope it keeps running because it might be a difficult problem to fix. But the idea is that when a failure occurs in our customers' hands or in our factories, it often is not expected or not desired, and we don't want that to happen again. So getting a fix there to do it is immense. So what can you do to minimize this immense pressure that can build up to get it fixed right now? Or is it just something we're going to have to live with? So what do you think? I'm sure everybody on this call has been in one of these circumstances where a customer calls and they have a failure and we need to fix this before we continue production. And by the way, it's Friday afternoon and we got to do it right now. You know, in my career, it's been Friday afternoon seems to be the time that you hear about a big problem. So what do you think? What can you do to address this pressure, as I'm calling it, to just do something, whether or not it's the right thing to do, but just do something? Or is it something we just got to live with? This gives me a chance to take a sip of coffee. See a bunch of people talking. Yeah, managing expectations. You know, Brian, when I first signed on and thought of myself as a reliability engineer, I didn't think of myself as a managing expectations kind of person. I did statistics, so there was a lot of barriers there. But what else? Yeah, I agree. Managing expectations and what it means to actually fix something. What are the steps and processes in an urgent situation? What can we do? And it might be different than when we have time and the line isn't shut down, but we have a failure we can address. We could do more due diligence, but how do we deal with this? Yeah, you know, my boss never understood get a full understanding of the problem. He's like, you're the engineer, you already know this stuff, just fix it. Or the technician is, hey, you're the expert on this equipment, get it running again. You know, and it's, yeah, and Keith, I think you hit the nail on the head there. It's discipline. Is that notion of if I fix it right now, if I fix it correctly now by doing the due diligence to understand what exactly failed, I won't be back out here in 10 minutes or in an hour to fix it again. Quote, fix it again. Some organizations get that. They understand that if I spend the extra time to understand what exactly failed and fix that, then I save time later. Yet there still are folks out there that don't get that. They just want it running. And they expect you to do the right fix. So part of this is that expectation is that, you know, I can bang a hammer down here all day long, but it may or may not actually fix anything. And these are, a lot of our equipment and products are relatively complex, to say the least. And so knowing exactly what to fix is not always obvious. You know, when it is obvious, when we know exactly what the problem is when we open it up and we fix it, we're good. Maybe we're a victim of our own efficiency sometimes. We fix 5 out of 6 problems real quickly because it's obvious. And then that 6th one is just everything looks great. We don't know why it's not starting. And we have to do more investigation and more checking and more evaluation. Not all failures are obvious. And so having those discussions up front, having that ability to say, hey, look, we both want the same thing. We want our equipment to operate, and we want it to work for our customers. By understanding what the real problem is, then we could do the fix once, and we won't be back again and again and again. And so it really is a bit of setting expectations in the discipline. The other barrier I've seen in organizations, and I got spoiled when I worked with Raychem Corporation and then later with Hewlett Packard Corporation. I was engineers in both organizations. Both companies had beautiful failure analysis laboratories. They had the scanning electron microscopes. They had X-ray equipment. They had CSAM equipment, which was a scanning acoustic microscope. They had microscopes and cross-section equipment and chemical analysis equipment. And one lab I was in Roseville, California, one of the HP labs, had probably, I don't know, a couple $1 million worth of capital equipment in it. It was phenomenal, the stuff they could do to understand and take apart a piece of equipment and understand exactly what failed. Coupling that with the capability, the ability to understand how to do failure analysis without skewing the results or damaging what actually happened, are often a problem. It's a barrier. We all can't afford a couple $1 million of equipment and highly trained technicians to operate it to do failure analysis. And one of my favorite pieces of equipment I ran into some years ago was called a squid. And I have no idea what it stands for, but it had the capability of visualizing current flow. So I was looking for a leakage current somewhere there was corrosion, but we couldn't see it visually. With microscopes and scans, we couldn't see the little traces of metal that were causing the short to occur. And this equipment was able to visualize the movement of current and identified exactly where that corrosion was and led us to a way to solve that. There's all kinds. We could do a whole year's worth of webinars on all these different pieces of equipment, and there's hundreds of ways we can take things apart. But some are very, very simple. A good magnifying glass oftentimes can tell you a whole lot, and you don't need a fancy microscope or a digital camera associated with it. Infrared cameras, IR cameras, are getting less and less expensive. They're more and more handheld based. They're easy to interpret. Basically, take an image of or focus your camera or the video camera or the IR video on your equipment, and you can see what's hotter than other things. And is that as expected? In factories, using an IR camera to look at boxes. Do we have the right connections? Are the connections solid enough that we have enough metal-to-metal contact to carry the current that's there? If not, it's going to heat up. Do we have the right components? Are they overheating? Or if you're looking at a circuit board, for example. You can even use IR cameras looking for insulation. I saw an application where you use a camera in your home to look for where you need to improve the heat loss. For example, now that we're getting into winter, where are you losing the heat in your home? And an IR camera can reveal what we can't normally see with a naked eye. So there's tons of equipment out there. So what do you do? If you don't have all this equipment, what are your options? What can you do with all of this? I have one of my favorite solutions, but how do you deal with this? Do you work to build a lab and then prove that it's valuable? Or do you outsource it or do with what you have and hope for the best? What are some solutions to getting the right failure analysis techniques for your equipment? And what are some of the barriers to doing that? I mean, cost is obviously one of them. And I'm noticing that the attendees, we got a good crowd today. A lot of people I've seen before and a handful of new folks, so welcome. Yeah, equipment rental. I mean, if I need I don't know if I'm sure you could rent a scanning electron microscope. I'm not sure about all the setup on it, but let's say it's a good microscope with a digital camera on it. I'm sure you can measure that or rent a infrared camera. And it might cost you a couple $100 to rent it for the day, but then by showing the value of those results, what you learn from that modest investment may be worth spending the $1,000 or $2,000 to buy your own camera. Yeah, and David, exactly. That was the one that's on my mind, is to find a good, and I'm putting this in quotes, good outside lab. More and more organizations, I remember locally here in the San Francisco Bay Area, IBM had a disk drive company or factory years and years ago. And they had an amazing failure analysis lab to support their production line and their development systems. And at one point, that lab got spun off to its own entity. And so I had all this equipment, all these trained people, and then they sold the ability to come to them with problems, and they would do the failure analysis for you. There's, I think, 4 or 5 different labs like that just in the San Francisco area. I know there's labs in Washington State, there's along the East Coast, in Southern California. They're all over the place. But finding one that has the equipment that can take apart and understand the types of problems you're running into. So if you need a lab that's good with contamination issues, then they need to have the chemical capability to identify what is this white powder on this product, corrosion elements and stuff. If it's more mechanical type things, can they make the right measurements? Can they do cross-sectioning, for example, and look at intermetallic layers for bonds and so on? But what I suggest doing with an outside lab is visit them when it's not an emergency, get to know them, what's their procedure, and if possible, put a blanket PO in place, right? Are they able to approach and solve the problems? And you're exactly right, David, is, here's the types of problems we're typically facing. How would you approach this? And if that completely stumps them, well, you probably need to look at a different lab that has expertise with your technology, with your types of products. And yeah, it might not be right across the street or next door, yet I find that having that relationship and getting the financial arrangements in place allows you to move pretty quickly when you do have an emergency and time is of the essence. And so it's part of it is understanding how to make the appropriate request to that lab so they know what you're looking for. And they have sufficient information so they can diagnose what's wrong with your product. And it is a partnership. When it's in-house, the lab develops expertise for your particular technology. You need to replicate that to some extent, or as much as you can with an outside lab, and build that ongoing understanding of your product's technology and types of failures, along with what they're capable of doing, what they're able to do to explore your products. It saves you the millions of dollars of capital expense and keeping staff online to do that. Yet I find spending a couple $1,000s a day to quickly get to the root cause of a problem, to really understand what exactly failed, can save you tens of thousands, if not hundreds of thousands of dollars in avoiding field failures, because you actually solve the real problem. And I like the idea of renting equipment and showing the value of it. If you work with an outside lab and get the expert, get the solution, compare that with what you could have done internally. And you almost always will find that the outside lab provides insights that you just couldn't get to without having that kind of equipment and expertise. So quantify that, show the value of doing those things. It makes the future FA work a lot easier. And then one of my favorite hurdles and problems, and I've seen this every single time I've been called in to do a root cause analysis, and we form a team or we get together with the experts for that particular part of the product or technology. And there's always somebody that crosses their arms, sits back and go, why are we holding a meeting? I already know the solution. Let's just go do it. And they may not even know what the problem is other than, hey, it doesn't power, and hey, it's up. Hey, and they go, well, it's always fill in the blank. Right? Now you add a little bit of pressure to problem immediately, and it looks very attractive to go with the expert, quote, expert, that says, I know exactly what the problem is, let's just fix it. And I have to say, on occasion, the experts that are right, they know from their design work or from their manufacturing work that this is an area that has a lot of risk. The symptoms are consistent with that failure occurring, and this is what we need to do to fix it. I've seen that happen more than once, and unfortunately, it's not always. It's not 100%, especially when you're spending a lot of money to implement a solution and a lot of time. You don't want to come back to it. And so a bit of due diligence, and this should be really preaching to the choir here, is a bit of due diligence to understand what the problem is before you create a solution, may save everybody a lot of problems and headache. Um, so. What do you think? How do you deal with the guy that sits in the back of the room and goes, I know exactly what this is. What do you say to them? How do you deal with that? How do you guard yourself from jumping to a solution? I think I'm as bad as anybody else at doing that. Um, and I think, Keith, you might have to retype your discipline in there again. Yeah. It's funny, Brian, it's that we always seem to find the time to fix it the second time. But that's the current situation. The first fix didn't work. We took a gamble. We're here to make risky decisions. We got a urgency. We got to move fast. Yeah. And if somebody says, I want to fix it right now, William, the idea of, well, where's your data? How do you know that? They trust me, I'm the expert. And I can fix it right now, which is oftentimes rather compelling. It doesn't have the data, it doesn't speak with the evidence. They may put a good logical story together. Yeah, the rifle shot or the shotgun type things. So, Keith, what do you mean by rifle shot? I've heard of shotgun where we just try a bunch of solutions and hope it works. What do you mean by rifle shot? Oh, maybe you're talking about where you try a fix and then adjust. Yeah. Oh, just one shot and you don't get multiple attempts. Well, what if it's not right then? But I'm going to come back. One of your comments here is that it's the psychology part of the problem. It's dealing with other people, right? And it could be the management team that wants it fixed right away. Could be an angry customer that's saying, hey, I paid good money for this. It should just work. Fix it. Or it could be the expert that says, oh, I know what this problem is. I saw this back in '82, and we just need to do this. But the idea here is, and it goes back to some of the other solutions, is what is the expectations? What is it to actually understand a problem so that we actually implement the right solution? How do we balance the need to fix it right away with the need to fix it correctly? And with that investment to avoid repeated fixes. In one organization I worked with, they tracked how many times they revisited similar problems and how much time they spent working on those things. And they use that as a very detailed kind of a financial analysis to say, hey, it's worth it to spend up to 8 hours understanding the problem before you implement even the first solution. And then spend enough time to fully understand it so that you don't revisit it again and again. And they use it as a trade-off. They say, hey, if we don't do a proper job doing failure analysis or the root cause analysis, we're going to come back to this over and over again. And so they started putting that together. Yeah, and Keith, you're right. I'm going to get into more of these disciplined approaches to solving these problems. And so part of it is setting expectations of what it means to do a root cause analysis. And it's not jump to the first solution that you have available. But what else? What other types of issues? I mentioned 3 of them here, is not having the FA equipment, the pressure to fix it right away, and the jump to solution things. What other kinds of things are you running at? Thanks for the explanation, Keith. Yeah, I was going to go off with the analogy that you shoot the messenger, but that's definitely not what you're meaning. Yeah, there's no strategy, just shotgunning. Yeah, we're going to try. We don't know exactly what the problem is, but it could be any of these 5 things. So let's fix all 5. And well, you know what that's like, is that 1 or 2 of those fixes could actually cause more damage, more problems for you long term. Could be adding more issues to your product. Software is great at that, right? We put a patch in and it creates a security leak, and we fix the security leak and it loses some functionality. So it's do the due diligence, get it right from the start. Let's talk about 3 different ways to approach doing root cause analysis. And there are different levels of sophistication, different ways of going about it. But I tend to use probably, well, I know when I get involved with root cause analysis, it's pulling from all of these 3 different kinds of approaches. The first one is speak with data, right? Get the information. So if I know it's not powering up, my computer, say, doesn't power up this morning, one of the things I can do is say, well, I can form a hypothesis. Well, is it getting power? Is the house providing, is the wall socket providing current, right? Are the lights turning on? So I create a very simple, quick hypothesis. Hey, in order for it to power up, it has to have power. Let's see if is it getting energized? And so I plug a lamp into it and turn on a light bulb. Okay, there's power out of the socket, right? Is the cord seated in the back of the computer correctly? Let's reseat that. And it's an iterative approach of thinking through the process or symptom and asking questions. And the more complicated products and systems that we have when they fail, of course, that gets way more difficult, right? It's harder and harder to ask good questions when there's so many different things can go wrong. But oftentimes, just asking the right questions helps us to solve problems. And understanding what it should do, the theory of operation, for example, helps us then to step through the process. And is it, at this node, I should see 10 volts when this state is going. I was standing behind the technician troubleshooting my heating system for the house, the heater in the house. And it's exactly what he did. It was, this should go here, this should happen, then this sensor should trip, and I should get 10 volts here that turns on the circuit for your fan to start blowing. He goes, I'm not getting 10 volts. And so then it was back up. What could interrupt that process? And was it a bad sensor or was it a bad circuit board? And he was able to get it to a point where he could say, if I change this part, it should fix part of the problem. Now, why exactly it wasn't getting 10 volts? He was working to the field replaceable unit, so he didn't go into detail on that circuit board. Yet when I called the company and ordered a new board, I also asked them what their process was. They said, well, we get most of these boards back and we do failure analysis to understand, is it a digital logic problem? Is it a trace problem? Is it whatever? And so they explained in pretty nice detail their process of getting at the root cause of this so that future designs wouldn't have the issue. This is opposed to a technician that comes in and just replaces 6 boards and 4 sensors and charges me all for that. Instead, this guy spent about a half an hour doing troubleshooting and understanding where the difference was between what it should do and what it is doing. And then recommended a board change, and that fixed the problem. That was last year, and it's still working. So part of this is just create a series of questions and then go test this, go measure it, go make those, get the data, and also challenge your operate. Yeah, and Dennis, I've run into that where we had a repair lab. I think I've told this story in previous webinars, but this repair lab got paid by the value of the components they changed, not by actually fixing anything. So they always replace the motherboard, excuse me, because that was the most expensive part. Even when it actually fixed something that was just a connector came loose. Just the other day, my wife's computer was in the shop, and the technician said, first thing we're going to do is we're going to reseat all the connectors. And if that's the problem, if that solves the problem, it's no cost. Just come pick you up a product. And if we do the troubleshooting and we find that it actually is a circuit board or something that we have to replace, we'll charge you for the parts and then the labor. I thought it was interesting. They weren't even going to charge us for opening up the equipment and reseating all the connectors. And they had all the special tools and techniques to open up. There's an iMac which isn't easy to open up at all. But they didn't charge us for that. And it turned out, it was 2 weeks ago, and the computer's still working. So if it was fretting, it might come back. But the reseeding actually cleared that problem, at least for now. So anyway, so create a series of questions. Test your hypothesis, test your assumptions. Another approach, and this is one that we use oftentimes in the development process to understand, do we have a robust product? Especially when you want a high uptime or a high availability type product. Do we have any single point failures? We may look for using this tool called fault tree analysis. So you start with a top level failure mode, say it won't power up. Well, what could cause that, right? Could be not plugged in, could be a bad cable, could be a bad connector, could be a bad power supply circuit board, could be a failed, all kinds of things within that circuitry and systems that we don't power up. Could be a bad switch. The power switch is bad, has failed or has gone intermittent. So we list all of these different ways it could fail. And then we go into, well, let's say if it's a bad switch. Well, it could be, it doesn't make contact anymore because the spring failed, or it's got corrosion, or it's got contamination. So it could be multiple things that could cause a power switch to not function correctly, which then causes the system not to power up. And it's thinking through all of those sequences of fundamental problems that occur. And it's a top-down kind of problem. It won't power up as our top level. Well, what could cause that to happen? And what could cause that to happen? And what could cause that to happen? Until you're down to the chemistry and physics, the fundamentals of things like metal migration or contaminant growth or oxidation or stuff that we remember from our physics and chemistry classes, kinds of issues. If you have the fault tree analysis available, it's a great tool to understand what are the things that could cause this particular problem to occur. Now, if you're facing a problem, it's also prudent to just think through, well, what could cause this to happen? And start asking better questions. Start checking those things off and testing those. And this is part of the troubleshooting process, this understanding that theory of operation, what it should do. And then if I see something going wrong, what can contribute to that? So this kind of thinking goes into call center menu trees for responding to symptoms customers are telling us about, troubleshooting equipment by technicians, and so on. It's an approach or tool that we use pretty consistently. The better the fault tree analysis, though, the better our ability to troubleshoot and to understand what we could test and evaluate and determine where the source of the problem is. So one more approach, and I want to finish off with this one. I have a number of slides to step through this. It's called an 8D problem-solving approach. And its forte, I believe, is in root cause analysis. Now, the nature of the problem you're solving could be a business problem or a design problem or an actual failure of your product or system. And I'm sure many of you have heard of 8D, and it's many, many different variants that they have. Yeah, and Hojat, you're exactly right. One of the issues is that we don't go deep enough in understanding the problem, whether we're doing the hypothesis-based approach or fault tree analysis type approach, even 8D. Oftentimes we say, "Oh, I know what it is. That symptom is almost always caused by this problem. Let's solve that problem." The issue is that we often leave out it's almost always caused by that. There could be many different causes. And it may not be a hardware problem. It may not be a software problem. It may be a customer expectation problem. We have the wrong design. We have the wrong advertising. So when you get to a problem that actually is not obvious and it's not a simple make sure it's plugged in kind of issue, um, a good disciplined approach is called 8D, 8 disciplines. And and actually the variations I see most often have 9 steps, but they still call it 8D. But the idea is that a problem arises. A customer calls and says, hey, we got a problem. This product isn't working. Or it's an issue in your factory. The line is down. Well, the first step is to gather the information, understand exactly what the circumstances, right? Is it an emergency and do we need to call 911, for example? Or do we need to respond to make it safe? Is it going into an unsafe condition? Or is there information immediately available that helps us to understand the nature of this problem? So for the first response is part medical in an emergency. Are people hurt and do we need to deal with that? And we should, and that should be a priority. The second is the equipment in a state that continues to pose a threat. So should we quarantine it, evacuate the building? What is it we need to do? And then third is preserve the evidence. Treat it like a crime scene, right? Put up the yellow tape if you need to, but don't jump in and start fixing it until you understand what the problem is. And that initial failure is where you may have heard strange noises from a different place, or there was a change in the material coming into the system, or there was something that could be related to the issue. It may not be. Yet if we miss it, when we come back at a later time, or we come back even an hour later, that information is lost, and it may be the key piece we need. So the first response is make it safe. The second response is contain it so it doesn't cause more damage. And the third part is gather information. Understand the environment and what happened, what's the circumstances that caused that problem. And I've seen it online where people are saying, well, all right, if it doesn't power up, what else is going on? You know, what's the surrounding environment like? What else could be contributing to this? And then they could help me solve the particular problem. So the 8D process it's a team-based approach. The idea is that no one person is smart enough or knowledgeable enough or capable enough to solve these trickier, more difficult problems. And it's based on we're better together than alone kind of idea. Basic ground rules are, one person speaks at a time, respect for each other, all of the basics of good meetings and meeting management. But it's also a focus on the steps of the process. And one of the strict ground rules is don't jump to a solution, right? It's a hypothesis. It's worth vetting and understanding. Let's get the data to make sure it is the right solution. Some teams organize as a core team where it's 2-3 people that it might be the reliability engineer, a key design engineer, and a manufacturing engineer to deal with and solve this problem. And then they pull in subject matter experts as needed to augment and supplement their team to drive towards the solution. Now, this step should actually be thought out prior to having a failure come up. Who's your response team? Who's the group that's going to most likely go do this? Many organizations have something like this in place. They know exactly who to call to deal with particular types of problems. And it starts that team formation. And then this is the part that often gets missed in organizations in dealing with problems. Before you start exploring different possible solutions, do we understand the problem? So what is this problem? What is this problem not? Right? Is not lists. This problem is blue. It happens on Tuesdays. It only happens when we're outside. The problem is not red. It does not happen in any other day of the week, and so on. in listing down and asking that question, what is this problem? What is the nature of this problem, and what is it not? Helps us to delineate where's the scope or boundary of this particular issue. Is it only with this one batch of material, or does it include multiple batches of these components, for example? And then this is the 5 whys. Let's dig down into why did this occur? What was the underlying layers of complexity that lead to us thinking through, like a root cause or a fault tree analysis? What are the underlying elements of these symptoms that we're seeing? What are the areas we need to explore? Then there's brainstorming, affinity diagramming, fishbone diagramming, ways to explore the many potential or possible causes of the issue that we're seeing. And then other tools to help us narrow it down and prioritize. What are we going to evaluate or test or implement? Yeah. And then in many cases, in bowing to this pressure to fix it immediately, is we need to contain it. We need to put a fix in with some verification that this problem is going to help us solve it, to get us in partial operation, to restart our line, but do an inspection step that we didn't do before to ferret out bad components. We may implement something relatively quickly to get us back into the game, get our products working again. But it's oftentimes, at this point, it's our best immediate action to get going again, yet it's recognized it's not the final solution. And this is where the discipline really comes in. We're only at step 3, and there's more work to be done to actually fix the problem, to solve the issue, to determine the root cause. And so the next step is do the due diligence. And the criteria that I like to use is that I can turn on and off this failure at will. I understand it well enough that if I use this at 10 degrees Celsius on a Tuesday with this batch of material, it fails. If I do it in other circumstances, a different batch of material or higher or lower temperatures, it works. And I have the understanding of why that actually occurs. I can replicate the problem and I can fix the problem. And the solution manifests itself as fixing it. Now, this is what I typically get at, is this is that fundamental understanding of what the real problem is. And then work out what the permanent corrective action is and make sure you understand what it is we're actually solving and how you're going to measure it. And then step back to make sure you're not causing other problems across the product or system. So risk analysis of some sort. Does this solution create other problems? And then lay out a plan, implement it, start measuring it, make sure it's implemented correctly. And as many of you know, doing a change to a system or a design is usually not as simple as just saying, oh, we're going to fix this, and there's documents to be updated, processes to update, getting rid of inspection steps that were done intermittently. Or I'm sorry, William, just your comment about intermittence. Yeah, they're trickier. But if it's a 1 in 10,000 iterations that I see this particular issue, if I can turn it on and off and create that intermittent issue, it's a level of understanding. I know in one case I had is that we had a cracked solder joint that was creating an intermittent at different temperatures. By just pushing down, just physically pushing the component down, reconnected it, and it would work. If I lifted the component just slightly, not fraction of a millimeter, the product wouldn't work. And then we took the component apart and saw that that was a cracked solder joint. And we could, with destructive, taking the component off, we could determine that it was cracked and knew exactly what the source of that intermittent problem was. But just running the system at room temperature, it worked pretty well. It almost never failed. And at certain temperatures, certain expansions, it would go intermittent. And when that circuit was called for, so it was tough to find. But we just started. We suspected bad solder joints, so we started just making sure all the joints were connected. And by physical force, made the connections, and we were able to find it that way. I think we were lucky in some regard. Then prevent it from reoccurring. What in your process of developing the product or validating your production line or working with vendors led to this problem occurring in the first place? And how can we take that lesson and implement it across our system so we can prevent similar problems in the future? And then celebrate. I actually was in one group that actually did the 7D process. They skipped the celebration part. You know, something as simple as a bit of pizza and a recognition that you guys actually solved the problem goes a long way. But also capture how valuable it was to do the right process and save and to implement the correct solution the first time. Capture how much that was worth to the organization. And yeah, pizza for engineers is not terribly expensive, and it goes a long way to recognizing the discipline they had to actually do the root cause analysis and the due diligence to implement an appropriate solution. And the last question I got for you is, one of the hurdles I've seen is people don't want to talk about failures. It's not just celebrating the solution to a problem, but when you find a problem, does your organization deal with that and recognize it and solve it in an appropriate way, making it safe to raise the discussion about failures? And I think that's part of the culture of organizations. If it's not safe to say, hey, there's a problem here, the customers are going to find them. And so part of this goes back to, how do you deal with failures? How do you talk about something that's not quite right? And so what do you, and I guess this is more a rhetorical question, but is there a culture where you actually celebrate failures? You realize that those are an ability to improve your product and processes. And if so, that's great. Yeah, field failure data is like gold. Well said, David. Yeah, and it's not to be ignored, it's not to be ostracized, but understanding why your product is failing helps you create better designs, to respond to failures more efficiently, and to create better products going forward. But if we just say, well, customers always complain, they don't understand how to use our product, is kind of sticking your head in the sand and ignoring a real opportunity to make improvements. And so the idea is that we all face challenges to doing root cause analysis. Failure analysis is just one part of that, but there's dealing with other people, different business priorities and customers' expectations. And then I outlined a couple different ways to approach this, and we often use a mixture of all of these things. But I think it was Keith that said it's discipline. And that, I think, is the key takeaway, is think through how you and your organization are going to approach serious problems. And I highly recommend the 8D approach, which is based on a team and with an intent to guard against jumping to a solution, but to truly do the root cause analysis, to fully understand the problem so that you can implement the appropriate fix or solution. And then implement it long term. And that takes discipline all across your organization. So it's something to aspire to and work to. And the best part is that working with failure analysis and all those wizardry tools that they have is always a fun part. But the reward is in really implementing solutions that help you and your organization meet your customers' expectations and or keep your factory up and running. But dealing with failures in an upfront, clean way is the heart of dealing with root cause analysis. So I think I realized I was running out a bit of the time there, so I went a little bit fast. You can find more about 8D and the variants of that with a simple Google search for 8 disciplines problem solving or 8D problem solving. And there's all kinds of information available. I think Quality One has got a really informative site. They also, I don't have any affiliation with them, but they also do training and consulting on it. Wikipedia's got a good deal on it, and a number of other sites do too. So thanks, Mark. I'm glad to hear you're using 8D. Yeah, and William, get a hold of Mark. He's got the experience already with it, but it is a promising technique, and it's based on common sense, yet it does enforce that expectation that we don't jump into failure analysis until we understand what problem we're trying to understand. So understanding the problem and then vetting your solutions to make sure they work, and an intermediate solution, a permanent solution that you fully work out, and then a long-term solution so you update your system around what caused the initial problem. So there's a couple different levels and players in that. So certainly appreciate all the comments and participation in it. That's pretty much what I try to do with each of these webinars, and it only works if you chime in, which you did, which is great. And so if anybody has any questions or more stuff they'd like to do, I'll stick around online for a bit. I know we're up against the timeline here. But also you can find out more about failure analysis and all kinds of stuff about reliability at accendoreliability.com, which I'm sure many of you are already familiar with. But also check out the podcast network, reliability.fm. Right around the end of November, we went over 400,000 downloads. And as of this morning, we're at 425,000 downloads. The pace of downloads is picking up tremendously. So appreciate all the support everybody's. And hopefully you're actually listening to them, not just downloading them. It's hard to tell from the send. But we have been getting some really nice comments and feedback on the podcast network. So be sure to check that out. Let's see. Yeah, Brian, I enjoy putting on these webinars. Obviously I like talking about reliability stuff, and hopefully it's helpful in the long run. And it's worth spending a little time talking shop with a bunch of people that have similar interests. So I appreciate you all chiming in today.